So you've also got to be able to handle momentum in 2 dimensions, momentum in 2D. So let's have a look at the tools you need to be able to do that and how that all works. Okay, so let's start with a sort of normal, simple example. And well, along here we've just got a ball move. Let's say it's a ball of mass m1 and it's moving along with some initial speed u1, and it's going to bang into another particle of mass m2. But let's suppose that initial one is at rest. So that at the moment is a very normal situation. And in the past we would have dealt with that by just assuming that they stayed in that kind of axis, that grey axis that I've drawn there, and then we can say momentum before is momentum after in 1 dimension. But supposing it hits it at a slight angle, so like a snooker ball or something like that, so that they kind of go off like this. Well, that's going to change things slightly. So this is still m1 now, and it's going at some final velocity v1. m2 now is moving off with not 0 velocity anymore, with some final velocity v2. And so now we're in 2 dimensions. And so how are we going to cope with that? Well, there's a couple of possibilities that are useful tools and that crop up in questions. Well, the first one is drawing a vector diagram to show the conservation of momentum in 2 dimensions. Well, this is basically very similar to doing force vector diagrams, except that we have the fact that the momentum before the collision is equal to the momentum after the collision. Here we are. This is the situation before the collision, and this is, of course, the situation after the collision. And we know that the total momentum before has to equal the total momentum after. Well, I can draw the total momentum before as an arrow, something like this. I'm sure you'll agree with me. Because if I call this, let's just call that, it's m1 u1, isn't it? This is the only thing that's moving before. Well, I'm going to call it p1 instead of m1 u1. Well, that has to be equal to the vector sum of the momenta of the bodies after the collision. In other words, when I grab these two here and add those vectors together, which is going to look something like this, that has to amount to the same thing as p1 in the sense of vector addition. In other words, I can do something like this. If I draw the vector due to the m1 v1 ball after the collision, well, that's moving sort of up, kind of up with something like this. So I'm going to put an arrow there, and I'm going to call that p2. So that represents the momentum of this object. But there's another body now, and that has a momentum kind of pointing sort of down at roughly that angle. I think you'll agree. Yes, that's this one. Well, that's m2 v2. I'm just going to call it p3, and of course I need to put an arrow on there. So in that way, I've drawn a vector diagram showing that the momentum before p1 is equal to the sum of the vectors, momentum vectors after p1, p2 plus p3. So you get the odd question using that idea. But let's look at it now in terms of equations, and let's look at it more mathematically. Well, first of all, we'll just trace back some kind of directions here so we can see the situation a little bit more clearly. Because after the collision, these are going off at some angles, so we ought to put those in. So let's call that θ1, and let's call this angle θ2. And what I'm going to now do is introduce you to a really useful fact. That momentum is conserved in any direction. Remember, think back again to forces. Well, when you're resolving forces, if you have a situation in equilibrium, the forces are balanced in any direction you choose. Well, it's very similar in momentum. The momentum before the collision is equal to momentum after the collision in any direction you choose. And if you think about it, that makes sense because forces at right angles can't affect forces perpendicular to them. So any direction you choose must have conservation of momentum in play. Well, that means we can write a couple of equations here. And so let's write a few. Well, let's first of all then choose let's call this the x direction, or the horizontal direction. And so, well, in the x direction, if momentum's conserved, well, before the collision, we've just got what I'm calling P1, or I'm going to write it fully this time, M1, U1, because that's the only momentum before the collision. Well, what's the momentum in the horizontal direction, in the x direction, after the collision? Well, we need the x component of this momentum and the x component of this momentum. So you might want to pause and see if you could write it down. What you should have is m1 v1 cosine theta 1 plus m2 v2 cosine theta 2. And in that way, we've written one equation that represents conservation of momentum in the x direction. Very useful. Well, now let's do it for the y direction. By y direction, I'm talking about this direction perpendicular to the x direction, because it's an obvious direction to choose. Well, this time, the momentum before, well, there is no momentum in the y direction, so 0 equals, and again, feel free to have a pause and write down the equation. Well, we've got plus m1 v1 sine theta 1 minus, because it's going down in the negative y direction, minus m2 v2 sine theta 2. And of course I could rewrite that second equation in a slightly more friendly way. I could put m1 v1 sine theta 1 equals m2 v2 sine theta 2. So that's it. That's the basic nuts and bolts of momentum in two dimensions. And really, most things amount to applying that. But there is another little trick, which I'm going to show you in the next bit. But just first, have a go at the couple of questions coming up and see if you can do them, and then check out the video solutions.